afternoon, everyone. So what we'll do is we'll be getting into double integrals and polar coordinates in a second. I want to do a few more problems from double integrals over general regions in 15.3. One of the things I noticed is sometimes the students have a lot of questions about when you have to reverse the order of integration. So I just wanted to practice a couple things. We won't have to go solve an integral, but the idea that every one of these problems, I just want you, can you just reverse the order of integration of some setup? The whole purpose behind this is sometimes when you reverse the order of integration, it's order, the problem's a lot easier doing dx dy versus dy dx when you set up the double integrals. So, here you go. I got a function from 0 to 9. 0 squared of x, function of x and y. And they wrote dy dx. Okay. Can you reverse the order of integration? Can you reverse the order of integration? We'll do a few of these. And once we're done with this, then we'll jump into the cool stuff, the polar coordinates, which is really neat. That's cool. But right now, just reverse the order of integration. So in the end, what's the easy stuff? You're going to have something like this. This is just going to turn into what? Dx dy. Do you have to reverse this? Remember, that represents the equation of the surface. Do you have to reverse this in any way, shape, or form? No. Whatever you see there stays. So if this said e to the x times y, I would write right here e to the x times y. If this said sine of x times y cubed, I'd write sine of xy. That does not reverse. So this stays. That stays. The only challenge is the what? It's this. And to do it, you really need to make a picture. That's the secret. Just draw a picture. So I'm going to draw a picture represent this. And this is where I write all over the place. So I'm thinking, okay, first of all, are these x's or y's? X's. So I'm like, okay, you're x's. Does everyone agree? I'm like, okay, those are x values. That means these are y equations. And if they're y equations, like y equals square root of x, y equals 0, I gotta think this is the top and this is the bottom. And I gotta think I gotta shade between these two equations from x equals 0 all the way to x equals 9. I got a shade between those two regions. That would be the bounded region. I guess the only challenge is what's y equals square root of x look like? We really do need to get a sense of this image to see what it looks like. Y equals square root of x, just go like that? Yeah. Awesome. So I'm going to do that. And how far do I got to go? All the way out to 1, 2, 3, 4, 5, 6, 7, 8, 9. And I'll stop there. Make a wall. Y equals square root of x. And y equals 0 is just right here, isn't it? So where are you shading? It's the key step. You're shading here. There you go. I'm not shading over here. I'm shading over here. All right. So far, so good? So now we're going to reverse it. You can do this by tilting your head and going like this. Who's my new top? And who's my new bottom? Right? And get everything in terms of x. These x equations. Or it's easier, we don't have to get the nut cramp like I was saying last class. We don't need to get a nut cramp. We can just think, who's my right-hand side and who's my left-hand side equations. So this will be your x equal to some right-hand side. I'll put x above. And that curve right there is going to be your equation x equal to some left-hand side equation. Cool. Well, let's start out. These have to be y values, and I have no idea what they are. So can you help me out? They have to be y values. The outer integral has to have values. What's that y value? 0. Y equals 0. What's that y value right there? 3. Excellent. How'd you get that? Substitute the 9 into the square root of x, right? So if this was 8, square root of 8. right? But a square root of 9 is a nice, neat 3. So we had to do that. Now this isn't going to be top and bottom like I wrote before. This is going to be your right-hand side x equation. This will be your left-hand side. Who's the right-hand side?
9.
Good job. It's that wall right there. X equals 9. So this is just a 9. Who's your left-hand side? This is where I get this all the time on tests. I didn't want to make, they think it's just 0. You go, no, it didn't go that far. What was the left? It was always getting bounded by this curve. And you got to solve for what letter? X. So what would be the left-hand side? There you go. There you go. I just want you to get that practice of reverse order of integration. So, okay, that was a dy dx one. I don't need to do that one. I want to do one like number 4 in the practice set. All right. So what if you have this? dx dy. We'll go the other one. It's just a couple of these before we get the polar coordinates. All right. So what if you got 0 to y squared, but you're going, I don't know, 0 to, I'll go to 2. And this says x cubed plus 5 times y. All right. And you got a dx dy. Can you reverse that? Well, obviously, we know the easy part. Does this change?
No.
That does not reverse at all. That stays the same surface. The order of integration will come out right there. This stuff. So this becomes dx dy, excuse me, dy dx. Alright. Now let's draw this. So I'm going to tear this thing out. These y's are x's. Alright, these are y values. Now your y. I'm going to shade from y equals 0 to y equals 2. The region bounded between are these x's or y's? Ah, that's an x equal, and that's an x equal. So I'm going to think you're the right side, and you're on the left side. These are going to be the boundary, and I'm going to shade between these two curves. That's not a curve, that's just a line. Shade between. Alright. So, what does x equal to y squared look like? That's one of those sideways curves like this, right? Now let's draw one of those here. There you go. There's x equal to y squared. Oh, that's the right hand side. Who's the left? X equal to 0, what is that? That's just a vertical line. Where is it? Right there. Maybe what confuses students when they see x equal to 0, maybe they accidentally think below. It's that line right here. Alright. There's x equals 0. There's x equal to y squared. And you're going to shade between it from what? Y equals 0 all the way up to y equal to what? Y equals 2. Right. So where do you shade? Am I shading in here or over here? In here. When I mean shade between, that means shade between the right and the left. Shade between them, shade between them, shade between them. There you go. Man, you got it. So as long as you can do problems like these two, you're fine. You can switch any way, reversing the order of integration on any problem. Is that what I'm doing that? Alright, so now, these got to be x values. I don't need this. Take that out of the way. What's these x values? So I'm already stumped. I need to know what this x value was right there. What's that x value right there?
4.
Excellent. How'd you get that?
2 squared.
2 squared. So there's 4. So it looks like we're doing 0 to 4 for x, right? Okay. This is going to be a y equation. Who's on the top? And who's on the bottom? The top is this guy. Right? You go, no, that's not it. I just wrote it there. This right here was the x equals y squared, right? Here's your top. This flat line. is your top. What's the equation of that flat line? Y equals 2. And who's the bottom? It's the curve. The bottom is not 0. The bottom is that curve right there. So my top is y equals 2. The bottom is, if you solve for y, what would you get? Square root of x. Right there. Is that what I got there? There you go. That's the secret. That's the secret to reversing order of integration. You can do one either way. I think you're good. And we'll go into polar coordinates. All right, this next section, polar coordinates. Do you recall doing polar coordinates in Calc 2? I mean, you hit it and that was it, right? Boy, is this valuable in calculus 3. Polar coordinates is so useful when your region of integration, remember I was just shading on the last few problems? When your region of integration deals with a circle or a portion of a circle. So I'll make sure to repeat that. This is a great section. When your region of integration is a circle, or just a portion of a circle, it could be a sector, or it could be a semicircle. Polar coordinates, doing double integrals in polar coordinates is way easier. I need to show you why. Alright. So let's just say this is your surface. Right? I call make it a plane. Z equals x plus y. And then we're going to find the volume underneath this plane over a disk centered at the origin of radius 2. Okay? So if we had to find this volume down and above by the surface, x plus y, but below by the xy plane, only projected over just a circle with a radius of 2 centered at the origin. We put this here, right? And let's just say we do dy dx. Look how crazy this gets here. I want you to see this. So we're getting the volume over what region did I say? Over a just a circle with a radius of 2, or you can call it a disk because we've got to shade everything inside of it, right? So I get the volume underneath this plane over that disk. I should say net volume because part of that might go underneath the x-axis. All right, so you get all that. And the radius of this is 2. We're going to see the benefit to using polar coordinates. Right now we're in y's and x's. You know what they call that? They call this Cartesian, in terms of the Cartesian plane, right? X's and y's, or rectangular coordinates. So you'll hear me refer to that. Rectangular coordinates, I'm talking about x's and y's. All right. Well, if we do this in the rectangular coordinate system, and I got to bound this, the easy part is the x's. What's the limits for x? Because this is just a circle, the radius is 2. That's easy. What's that? -2. This is the crazy part. How do you get the equation of that top semicircle? And that's the circle, everyone, centered at the origin with a radius of 2. That's x squared plus y squared equals 4. So if you haven't seen circles in a while, these are what circle equations look like when they're centered at the origin. You go, well, if they got shifted, it's a little different. Don't worry about that now. Most of these are just centered at the origin. So hey, just to go on and on and on, what's the circle with a radius of 3 centered at the origin?
9.
X squared plus y squared equals 9, right? Or a radius of 5, x squared plus y squared equals 25. You'll start seeing a lot of circles from here on out. I guess since I shaded inside, mathematically, I probably should put that then, right? Because I've shaded everything inside the disk. You know, region of integration. I'll put that. But how do you do this? How do I get that top limit? That's the top curve. I'd have to solve for the letter y, right? And this is where it gets a little weird. So when I'm going to solve for that top y right here, this y would equal, subtract the x squared and take the what? The square root of both sides, right? And what would be the bottom curve? The bottom semicircle. That would be my bottom portion. This will be my top. Oh yeah, I'll put that right here. And what's the bottom? Minus. The minus, very good. A negative square root of 4 minus x squared. That bottom semicircle would be the bottom. But I want to just you to have this in your notes just to look at and go, ugh. You follow me? Hey, now go do the math. Well, maybe it won't be too bad because you get x squared over 2 or an x all that. It still gets nasty with the what? With the radicals. I used to type this into a TI Voyage 200, everyone, and the thing would just run and run and run in like an infinite loop. It would never give me the solution because I'm typing everything in rectangular coordinates. So when your region of integration is a circle or a portion of a circle, you definitely want to go polar coordinates. You want to use polar coordinates because it's so much easier. So the first thing is, step 1, if we're going to want to use polar coordinates for any disk or anything projected over a disk or a portion of a disk, so can I erase this? Cool, we get this out of the way. And we can come back to this. You and I had to derive what in the heck we're going to replace dx dy with. So if we go polar coordinates, everyone, this is called an infinitesimal polar rectangle. All right, this from here to here is the radius. So when you see my infinitesimal polar rectangle, that little tiny rectangle right there, we got to figure out what does dx dy equal. You see that tiny arc? So does anybody remember the equation for an arc? The equation for an arc of a circle, they called it S, was radius times theta. All right? But this theta in here, everyone, is infinitesimal. It's just infinitesimal as well. So I'm going to call this angle right in here, how about d theta? All right? That'll be d theta. What can I call that little side right there? This little side to the rectangle. It's a little portion of this radius r, so I can call that dr. And you got to help me out. And what can I call this little tiny arc right there? And we'll find out area of this infinitesimal polar rectangle. What would be the equation of that tiny arc right there?
ds.
Well, according to this, it would just be what? D theta times the letter r, right? Is this what this, like here, if I was on a circle, and this was theta, and when you go, what's the length from here to here? It would equal r times theta. But here it's really cool. So when I'm just going to draw an arrow here and just go, this little portion right there, that little arc would equal r times d theta. Similar to this. Cool? So, in the end, what is the area of that infinitesimal polar rectangle? Now I'm going to shade it in. That little guy. Do length times width. We call it a polar rectangle. What's length times width? Even though it has that little tiny arc to it. What would you get? Dr, d theta times a what? Times an r. So put this in your notes, everyone. This is going to be equivalent to the dx dy we had before. Or the dy dx. Every time you go polar coordinates, we're not going to write dx dy. This is that dA. I'll put that here. Just leave this up the whole class. This is your dA. Remember how dA would always equal dx dy or dy dx? When we go polar, what are we going to use? Dr d theta, but don't forget what letter? R. So you'll be saying that over and over as a reminder. Don't forget to put that little letter R. Does anyone see how that emerged? Because that's what comes out of that in terms of an infinitesimal polar rectangle. We're saying that's dx dy in rectangular coordinates. But if we go polar, you got to put an r d theta in your image. Cool? If it helps everyone, it sounds silly, but sometimes it helps a student. Just think like a pirate. You know, like the pirate who goes RDR. You know what I mean? Like RDR. Just think of that when you go in polar coordinates. Think like a pirate. So you don't forget what letter.
Oh.
That R. RDR. It's RDR d theta is what we're going to use for the dx dy. Okay. So, can you help me do this? We're going to do a problem just like that. What was it projected over? The entire disk with the radius of 2. And there's the circle with the radius of 2. And you got to evaluate this integral projected over that region. find the volume underneath this surface over that region. We don't want to go Cartesian, do we? We want to go what? Polar. Well, first of all, what am I going to put in place of that? What am I going to put in place of this? This becomes what? RD theta. Very good. Here, don't forget your RD theta. But I can't leave this, can I? And we're going to have to replace that x with something, and we're going to have to replace that y with something. Don't worry. Don't think the problem's getting more complicated. This problem's going to get a lot easier. So when we have to put something else on the board. When we convert to polar coordinates, what does x represent and what does y represent? To do that, all we need is a nice right triangle. So I can put it here. You know what? I think I'll put on this board here first, and I'll transfer it to here. This is all we need to go into polar coordinates. So would you just build a triangle? All right. 90 degrees, that's the x-axis, that's the y-axis. Call this length x, call this length y, and call this radius r. And put a theta there. And do a little SOHCAHTOA, and you'll know the conversions. Okay?
R cos theta x.
So cosine of theta is x over r. So x is equal to
R cos theta.
r cos theta. Radius times cosine theta. SOHCAHTOA. What's sine of theta?
Y.
Y over r. So what's y equal to?
R.
R sine theta. This is all we need. This is what we're going to put in place of the x and y. Now we need one more equation. Everyone, can you just do Pythagorean theorem for me? What's x squared plus y squared?
R squared.
Alright, cool. So if we get an x squared plus a y squared, we can just replace that with a r squared. I will leave this up all class. The reason I wanted you to do that with me, so if you're ever stumped on a test, it could be the final exam. You go, oh, I want to go polar on this. I'm dealing with the region of integration that's a circle. You can generate that right away with SOHCAHTOA trigonometry. Convert to polar. Hey, if you want one more equation, can someone give me the equation for theta? Just if you're curious. I don't think you'll ever need it. It's just a gauge. You know what theta would equal?
Tan
Inverse tangent of y over the x, right? If you want an equation for theta. Cool. Hey, all points in polar coordinates, that point right there will be plotted as radius comma theta. We always plot it as r comma theta. So polar coordinates, I'll put this here. Everything is plotted as r comma theta. And let me draw that triangle again. Theta, y, x, r. What's my main equations? X equals r cosine theta. Y equals r sine theta. And x squared plus y squared equals
R squared.
r squared. There we go. And if you want to put that one as well, you can. We'll only put it down if we need it. Okay. Let me get this mess out of the way. There's your region of integration. And you're only going to project this over that disk right there. So we're going to have to set that up here, right? We'll come back to that. You draw that circle right there. So we're going polar on this. That would be crazy in rectangular coordinates. We didn't forget our RDR. What can I put in place of that x? R cosine theta. And what do I put in place of the y?
R sine theta.
R sine theta. So R cosine theta plus R sine theta. What else was sitting right here? The pirate RDR. So this is going to be your r's, your limits of integration for r. That's going to be easy. This is going to be a theta. That's going to be easy. I say we start with theta. Anybody know what theta would have to be? Put it in radians to do a full circle. Remember, standard position, start here. 0 all the way to what? 2 pi. You got it? In fact, won't that always be the case if you got a full disk? Polar coordinates, piece of cake. What's your radii though? So for radius, everyone, you got to go from the pole, which is the origin. In this shaded region,
Negative.
I went from 0 to 2, 0 to 2, 0 to 2, 0 to 2, this whole region, right? 0 to 2, 0 to 2, because in terms of a radius, when we're doing polar coordinates, you go the distance from the origin out to the edge of the curve. So this will be from 0 to And I'll write that really big up here. Well, look what we have now. This will be way easier to solve this problem. R cos theta, R sine theta. A lot easier than going Cartesian. dr d theta. I did this on purpose. What did I forget? R. R dr. You can put that R here too. So we'll solve this, and when we're done solving this, I'll put this on the board so you can say, what do we always do in polar coordinates? We always put the R dr d theta, and we get everything in terms of R cosine theta and R sine theta. Nice. Now let's work the problem. What do we get for this answer? What is the volume under that plane or that region? Can I break this up into two separate intervals? The rule of thumb, there's two things I have to hold. These have to be 4 numbers, are they?
Yes.
Okay, they're 4 numbers. Can you rewrite this as just R's times just stuff and theta? I think you can. I'm hearing, yeah, I think we can. Does everyone see this? See, I split it up if I can, just to avoid doing the iterated integral. Can I factor out an R? So if I factor out an R, what do you have? That's how I would approach this problem. You factor out an R, what do you have in the parentheses? Cosine theta plus a sine theta. Now I can multiply this R to this R, and what do you get?
R squared.
R squared. So then I am going to split this up. I just think it'll be easier. Here. I'm going to do 0 to 2 pi of cosine theta plus sine theta d theta. And I'm going to multiply that to the integral from 0 to 2 of the R squared dr. This is how easy this problem is going to be. Way easier than if we went Cartesian. That's my point. I know you know how to integrate that. This doesn't even need a u sub. Right? Hey, I'll start here. What's this?
1/3 R cubed.
1/3 R cubed. Go from 0 to 2, you get 8/3. Okay, we're going to multiply that number to this. What's the integral of cos? Sine. What's the integral of sine? Alright. You got to go from 0 to 2 pi. Alright. So I get 0 minus 1 minus 0 minus 1. Now take this entire number right here and multiply to that. What do you get? What's 0 minus 1 minus 0 minus 1? Uh-oh. And we're like, did we make an error? Well, we did make an error. Right? This is correct. We did the antiderivative correctly. We know what the sine of 2 pi is, and the cosine of 2 pi, and the sine of 0, and the cosine of 0. 0 times 8/3. What's the answer to this integral?
0.
So what's that integrate now? I kept saying the word volume. Well, it's really net volume, because what can happen? Over that what? Over that region I had, the plane z equals x plus y might have done what? And half of the plane could be underneath the xy plane, and the other half could be above. And that's why it's coming out to be 0. I didn't want you to freak out when you get zeros or negative answers like, did I do something wrong? No, that's exactly what's happening. Cool?
And how do we find the true volume?
Oh, for this?
Yeah.
They'll never actually like find that true volume for that unless they ask you to, they give you a surface that's totally going to be above the xy plane. So if they give you something that's always above the xy plane, then they can ask you to find that actual volume of that. So I'm trying to think of some example like something that you know that's always going to be above that. Like I'm thinking of something like that. Z equals x squared plus y squared. Isn't that a paraboloid? I'm going to draw this just so you can see it here. And we go, all right, that's a paraboloid. And let's say you had to find the volume of the solid formed by this paraboloid. I'm going to go up to like z equals 9. And underneath that plane, it's bounded below by this paraboloid. So it's bounded above by the plane z equals 9, but bounded below by this surface. We can actually visualize that. We can see it's what? It actually has a certain, actual volume to it. Nothing's below the xy plane, and we're able to solve that. So that's where they would ask that. Good question, though. So if they ask you to find the actual volume, they're giving you something that's going to actually be above that xy plane. great job. Hey, on that note, can we do this? This is not a bad problem at all. Aiden, I like your question. Can you help me find the volume of that? I do want to point out, this is the volume of a solid bounded at the top by the plane z equals 9. Can you tell it forms a circular disk? Cool, it's the plane z equals 9 now. It's just because it's a circular paraboloid. And it's bounded below by this surface right here. Remember, that's the surface. So this is below. This right here, I'm going to put an arrow. That's z equal to x squared plus y squared. And the top portion is the what? Z equals 9. Cool. So I'm going to write this up. Done my interval. Can you think about what's this getting projected over? I mean, this is the region of integration. So can you think what this projects onto the xy plane? Think of it as a projection, the shadow. What is the projection of this onto the xy plane? Can you all see it's a circle? It's the widest circle ever encountered by that solid. And they call that the projection. So I'll put that here. This is that projection. Can you all see what that circle's radius is? I don't know if you can. What's the projection onto the xy plane? It's a circle. Or I should say disk, because of everything inside of it. Let's call it a disk. What's its radius though?
3.
Amazing. You all knew. I didn't even do any algebra. You know that. How did you do that? How did you know it was a radius of 3? Because you set this number equal to that. Do you follow me? So I'm going to do that. They knew this because they actually told, when does x squared plus y squared meet the equation 9? When does x squared plus y squared, that's a z, equal z equals 9? So x squared plus y squared must be equal to 9, giving you a radius of what? 3. So this is the projection. So when we set up our right there. When we set up our region of integration, we're talking about this. So already I know we should do what? We're going to go polar eventually, right? Because of region of integration. But that's just going to set this up. What goes here? This is the what? The surface. But the surface, everyone, do you notice something? It's the surface, that region that we're talking about, it's bounded between the what? Between the 9 and the what? The x squared plus y squared. So I would have to write that here. Right?
Mm-hmm.
Oh, this, I would have put this right here if I was talking about this stuff here. But to talk about this here, Aiden, I gotta write, we're talking about the 9 subtract the x squared plus y squared. You follow me? That's how we gotta think. Does that make sense? And just to be, so you can, if you want to make a comparison and put it in your notes, you go, if you were getting the volume underneath this surface over that region, oh yeah, this would have just said x squared plus y squared. Because that's that actual surface. Now, you ready to go polar? Here, I'll just put a dA here. dA means, hey, you can stay Cartesian, or you can go polar. Let's go polar. What would this turn into? Go polar, all right. You all agree 0 to 5? What's the radius? 0 to 3? Right? D or D theta, what letter I need? Automatic R, right? I already R on the part, so I'll put it in front so it stands out. There it is. Now, what does this become? 9 minus, I need some help. What would you put in place of that? Brilliant. Did you hear this? He used this. X squared plus y squared is r squared. So he wrote 9 minus r squared. The r's out in front, so it gets distributed. It's not a bad problem at all, is it? This will give you the volume of that solid. Isn't that cool? That polar coordinates is awesome. It's so easy when you're dealing with these region of integrations that deal with this. Well, you know the nature of this. Many of the shapes we've seen so far have these cross sections that are circled. Think of a sphere. Don't think of the projection of a sphere onto the xy plane. Oh, circle. Circular paraboloid. Circles. So that's why polar coordinates is going to be like huge, huge help in working these problems. All right. 9r minus what? R cubed. Give it 2 pi. You already theta. Question for y'all. Can I break it up? Can I split that up? I can? Can I write this separately? It's got 4 numbers. Check. I like to split it up if I can. Remember, you can do everything as an iterated interval, but I will split this into 2 separate single integrals. Do each one separately and multiply them in the end, if I'm able to. You could do what the rules are. Number 1, these got to be 4 numbers. Does that work out? Check. The other rule is you got to be able to write this separately as thetas and r's. I can.
Yeah.
I'll have the 9r minus r cubed dr, and what will be the other part? Times up d theta. Do you all agree? So I'm going to do that. I'm going to set that up right now. 0 to 2 pi d theta. Heck, what's that interval? I'll drop it a little bit lower so everyone can see this. This is the beauty of this. I mean, you will not need much room to do this. You'll compute that, then you'll multiply to this interval from 0 to 3 of 9r minus r cubed dr. And no u subs needed or anything. I know some problems don't need a u sub, but here you don't. What's that interval? That becomes a theta. And when you plug in a 0 and a 2 pi, what's 2 pi minus 0?
2 pi.
2 pi. Boom, that's done. Now multiply that to, what's the integral of 9r with respect to r? 9r squared over 2 minus r to the 4th over 4, and go from 0 to 3. So that's 81 over 2 minus 81 over 4. Here's my answer. 81 over 2, 81 over 4. What is that though? I mean, what's 162 over 4 minus 81 over 4? 81 over 4. And then 81 over 4 times a 2.
162 over 4.
81 over 4 times a 2 pi becomes you should get that after all that. Do you agree? Yeah? Cool. I got you to back me up. Right? This would have become 81 over 4. But then when a 2 and a 4 makes just a 2 there. Cool. There it is. And that's the volume. So Aiden, I love your question, but when they ask that, they're being very specific. They're giving you some shape that's above the xy plane. So giving you some shape that's above there. Does that make go with that? Nice. I'm thinking, I guess Aiden, we could still do it. I'm trying to think, like, even if you had a, because I love your question. What if it was a paraboloid that was sticking upside down, and then it stopped down here at like z equals -3. Now let's just say this was z equal to -x squared minus y squared, plus 1, 2, 3, plus a 3. And this bottom thing is, you can still work it though. Thinking, I gotta do this, subtract that. I'd have to take this, subtract that in terms of my surface right there. Does that make sense? You'd still be able to get that solid. As long as when we write it here as top minus the bottom, it's always going to work out to give you the actual volume. Cool?
Couldn't you do it with any shape as long as you just divided it along the xy plane?
There you go. That's exactly right. You
Two
cut
separate
it off,
problems.
do 2 separate problems, and add those 2 portions together. Brilliant. That would work as well. So very good point. Fred says as long as you work as 2 separate integrals above the xy plane, below the xy plane, but then you'd have to know exactly where that surface hit the xy plane, right? But here, if you just had something like this, shifted up 3 notches, this was down 3 notches, and probably, when I set this up, I have to do just what? The top one minus the bottom one, which leads into something, everyone. We're going to get to after polar coordinates. You go, why don't you just set up a triple integral? So it sounds scary, but it's not bad at all. You see what I just wrote right here? I'm going to go a little bit above it, and go like this. this is the same as, put a 9 here, put this down here. We'll put dV for volume, and just put a 1 here. And what would be your first step? Because this would be like now dz dy dx. So what's the integral of 1 with respect to z? Z. And then you plug in a 9, you plug in this, and you subtract them, and you get this, don't you? Does that make sense? So we'll do that in a second, but this is a great problem you were talking about. I'll get this out of the way. We're saying, now we see a need that you can actually write things as triple integrals. And we're saying this could be the triple integral of 9 minus the x squared plus y squared. I'll put a dv here. Whoops. Triple integral, this would be the 9, this is the x squared plus y squared, and I'll just put a 1. So triple integrals of 1 find volume of solids. Triple integral 1, because your first step is, think of this as dz dy dx, right? dz dy dx. What's the integral of a 1 with respect to a z? Just a z, but what do you plug in there? You plug in 9, you plug in the x squared plus y squared, and you subtract them, and it turns into a what? A double integral. Does that make sense? Cool. So that's where we're going with it, but don't worry. Triple integrals, they don't get to that until section 15.6. I'll make sure to work one of those though before you leave today, so you get a chance to work with that. So does that make sense? This right here is equivalent to this. Cool. All right. So with triple integrals, can you eventually just keep doing polar coordinates? Yeah, but once you get it down to how many? A double integral. You all are good. Now I'll make sure we do another one before you leave with the triple integral. All right. I want to try this one. They want you to find, okay, they said evaluate. Evaluate the iterated interval. All right, I'll just write integral. They just put a d there. Cosine of x squared plus y squared dn. And here's d, where d is bounded by the semicircle x equal to the square root of 9 minus y squared. And the y-axis. Okay. We gotta evaluate that interval. Hey, you can go back to what you asked before. I think we still gotta treat that as net volume because I don't know what that surface is doing. It's equal to that, right? And it might dip below the xy plane and stuff there. We'd have to know what was happening. So who knows if we're going to get a positive or negative answer out of this right now. We'd have to have knowledge of that surface, wouldn't we? The way this is set up. So they're not asking for volume, they're just saying evaluate the interval. What is that? We know when you get y equal to square root of 9 minus x squared, that's the top semicircle, right? So what does x equal to square root of 9 minus x squared look like? It's a semicircle. Andrew Outstanding goes, it's on the side. So it's over here. So this is that region of integration. This is D. He says it's over here, and the radius is what? Alright, that's here. Does anybody know what we represent the part over here? X equals negative that. So you'll start seeing these more and more often. If it's y equal to, it's what? The top semicircle. If it's x equal to, it's on the side. Cool? So where am I shading? They said D is bounded by this semicircle. We know it has a radius of 3. And what was the equation? And the y-axis, which is where? Is that not good enough? Sometimes people read this and you're taking you're in test mode, and you're just reading the problem. The minute you see this, people just automatically say, "Oh, semicircle up on the top." because it was x equal to this, we're thinking this one and the y-axis right there. Does that make sense? So let's shape it. Now, what do y'all think? Do you want to stay Cartesian? No way. That's a portion of a what?
Polar.
How about this? Polar, go polar. Let's go polar on this, baby. Unless you like putting square roots and stuff, right? Square root of 9, no. Let's go polar on this. Okay, so I'll start out. Before I forget, what letter? R. RD theta, right? The pirate, RDR. RDR. I'm going polar, RDR. If you ever go, why are we doing that? Students will always ask me like a month later, why do we put that R? It always gets back to that. That's why I want to keep that up here. You can have an idea why we have to put that. All right. Cosine stays cosine. Any suggestions for this though? R squared. Right. Hey, if it just said cosine of x, and any little I would have written cosine of r cosine theta. Right? If it just said cosine of it. If it said cosine of y, I would have had to put cosine of all that. But when you get this x squared plus y squared, we can just put the r squared there. Cool. All right, we got that. Ooh, the radius is going to be easy. Do you all agree it's just 0 to 3?
Mm-hmm.
Look at the shaded region. From here to here, 0 to 3, 0 to 3, 0 to 3, 0 to 3, 0 to 3. That's how the r is measured. From the pole, they call it the pole. The pole is the origin. From the pole out to the edge of the curve. It's always 0 to 3. Can you help me with theta though? You got to think back to trigonometry. That's the, I love that. You just go from negative pi over 2 all the way up to pi over 2. Remember in trigonometry we rotated this way? We always rotated this way. So that's what we're going to have to put. Negative pi over 2 to pi over 2. Is there anything else I could have used? Because you got to think lower limit, upper limit, right? The only other thing we could have used is, I guess we could use coterminal angles. If I use 3 pi over 2 here, what do you got to use there? 5 pi over 2. Does that make sense? You got to think how it rotated. 3 pi over 2 to a 5 pi over 2, because this has to be the upper limit. That value has to be higher than this, true? Yeah? Is that it? Oh, cool. Question for y'all. Let me break it up. You can. It's funny. We can't always break it up. We get that, but many times in polar coordinates, you can split this up into two.
No, but didn't you say to do iterated?
What was that?
He said to do an iterate, right? Iterated integral.
Oh yeah, they wrote iterated integral.
Yeah.
They wrote that. Doesn't mean we have to do it.
Okay.
I love his question when he said, when I read the problem from the book, it said evaluate the iterated integral. And iteration means we got to do the innermost and the outermost. We don't have to do that in an iterated manner if we're allowed to split it up, right? By the way, you still know how to do an iterated integral, right? You do this one with respect to r, then you break out the other one. But I love when I can just what? Split this up, which can you tell I can? This is just a what? D theta, that's going to be easy. And what's the r part? I can break this up because I got 4 numbers. True? And I can break it up into thetas and r's. As a product, See, what's that?
Just theta.
There's a theta. This doesn't come out to be 0, does it? Be careful. What's pi over 2 subtract negative pi over 2?
Pi.
That's your pi.
Uh-huh.
And here's my reason I like to split them up when I can. Does that involve a u sub? That's my point. If you get involved in a u sub and you got a double integral on it, it can get really confusing, right? That may annoy you. So I want you to be very comfortable going, hey, I'm going to break this thing up. I will just do my u sub. U equals the r squared, right? What's du?
2r.
2r dr. So 1/2 du equals
R
r dr. We got a few u subs with these integrals in sections 15.4 and 15.5 and 15.6, etc. I want to go that. All right, let's put it in here. Go in here. What gets knocked out? The r and the dr go away. Now you have the cosine of what? Cosine of u. I think last class, a lot of you like to wait till the end. You resubstitute, so I'll do that. What's the integral of cosine u?
Fine.
Sine u. Now resubstitute. What was u again? R squared? And you gotta go from what to what? 0 to 3. So I get pi times, ready?
Shouldn't there be a half?
Yeah.
Half?
Oh, and a half, you're the best. Now let me put that right here. I gotta remember that 1/2 right there. Alright, thank you. And everyone else, thank you. They're like, don't forget you got a half right there. This is half cosine u du. And I'll put my half right here, and I'll put my half right here. So inside this interval, I get 1/2 of what? Sine of
9.
9? No, just leave it like that's 9 radians. That's an irrational number. Minus, at least we know what's sine of 0.
0.
What's the answer? And I'll put the answer right up here. Looks like we got pi over 2 times up.
Sine 9.
Sine 9. That's it. Pi over 2 times sine 9. Hey, when you get answers like this, pi over 2 times cosine 9 minus 1, you can just leave it like that. You can leave it like that, that's fine. Did I go that? Nice. Hey,